Control wiring is used to transmit signals to and from control devices, such as switches, relays, and controllers within a control system. Instrumentation wiring is used to connect sensors, transducers, and other instrumentation devices to a control system or other measurement and monitoring equipment. For control wiring, conduit can be filled to 60%. Current carrying conductors do not need to be derated for this fill percentage. Conduit containing instrumentation wiring can also be filled to 60%. Data cables, speaker cables, fire alarm cables, fiber optic cables, and low voltage switching cables can be installed in the same cable tray as instrumentation wiring without any trouble. Now let's dive into a more detailed explanation of each of these topics, starting with control wiring. Control wiring forms the nervous system of many automated systems, relaying signals between control devices to execute specific actions. These wires are typically used in applications where direct control over equipment is needed, such as starting or stopping motors, opening or closing valves, or activating alarms. The types of signals carried by control wires can vary widely, ranging from simple on or off signals to more complex analog signals that represent varying degrees of control. For instance, a control wire might carry a 24 volts direct current signal to activate a relay, or a 4 to 20 mA signal to control the speed of a motor. The selection of the appropriate wire gauge for control wiring depends on the current it will carry and the distance it will travel. Larger gauge wires are needed for higher currents and longer distances to minimize voltage drop, which could affect the performance of the controlled devices. Insulation is another critical factor to consider. Control wires are often run in environments where they may be exposed to moisture, chemicals, or extreme temperatures. Therefore, the insulation must be able to withstand these conditions to prevent shorts and ensure reliable operation. Common insulation materials include polyvinyl chloride, polyethylene, and cross-linked polyethylene, each offering different levels of resistance to environmental factors. Proper termination and labeling of control wires are essential for easy troubleshooting and maintenance. Wires should be securely terminated using appropriate connectors such as crimp-on terminals or screw terminals to ensure a reliable electrical connection. Each wire should be clearly labeled with its function and destination to facilitate identification and prevent errors during maintenance or repairs. Now let's look at instrumentation wiring. Instrumentation wiring plays a crucial role in measurement and monitoring systems, connecting sensors and transducers to control systems or data acquisition equipment. These wires carry signals that represent physical parameters such as temperature, pressure, flow rate, and level, allowing for real-time monitoring and control of industrial processes. Sensors and transducers convert physical parameters into electrical signals that can be transmitted over instrumentation wires. For example, a thermocouple converts temperature into a voltage, while a pressure transducer converts pressure into a current signal. These signals are then transmitted to a control system or data logger, where they are processed and used to make decisions or generate reports. The accuracy and reliability of instrumentation wiring are critical for ensuring the integrity of measurement and monitoring systems. Noise and interference can corrupt the signals carried by these wires, leading to inaccurate readings and potentially affecting the performance of the control process. Therefore, shielded cables are often used to minimize the effects of electromagnetic interference. Shielded cables have a conductive layer, such as a braided wire or foil, that surrounds the inner conductors and is grounded to provide a path for unwanted noise to dissipate. The routing of instrumentation wiring is also important to minimize noise and interference. Wires should be kept away from sources of electromagnetic interference, such as motors, transformers, and high-voltage cables. They should also be routed in a way that minimizes the length of the run and avoids sharp bends, which can increase the susceptibility to noise. As with control wiring, proper termination and labeling of instrumentation wires are essential for easy troubleshooting and maintenance. Wires should be securely terminated using appropriate connectors, and each wire should be clearly labeled with its function and destination. This is particularly important for instrumentation wiring, as the signals carried by these wires are often critical for process control and safety. Now we'll cover conduit fill. Conduit fill refers to the percentage of the cross-sectional area of a conduit that is occupied by conductors. The National Electrical Code, or NEC, specifies the maximum allowable conduit fill to ensure adequate space for heat dissipation and to prevent damage to the conductors during installation. According to the NEC, the maximum allowable conduit fill for conductors is typically 40% for 3 or more conductors and 53% for 2 conductors. However, for control wiring and instrumentation wiring, the NEC allows for a higher conduit fill of 60%. This is because control and instrumentation wires typically carry low currents and do not generate as much heat as power conductors. The higher conduit fill percentage allows for more efficient use of conduit space, reducing the overall cost of the installation. To calculate the conduit fill percentage, you need to know the cross-sectional area of the conductors and the inner diameter of the conduit. The cross-sectional area of a conductor can be found in the NEC or in manufacturer's data sheets. The inner diameter of the conduit can also be found in the NEC or in manufacturer's data sheets. Once you have these values, you can calculate the conduit fill percentage using the following formula. Conduit fill percentage equals the total cross-sectional area of the conductors divided by the cross-sectional area of the conduit multiplied by 100. It is important to note that the conduit fill percentage should not exceed the maximum allowable value specified by the NEC. Exceeding the conduit fill percentage can lead to overheating of the conductors, damage to the insulation, and even fire. Now let's discuss dirting. Dirting refers to the reduction of the ampacity of a conductor to account for factors such as high ambient temperature or the presence of multiple current-carrying conductors in a conduit or cable. The NEC specifies dirting factors for various conditions to ensure that conductors do not overheat and cause a fire. For control wiring and instrumentation wiring, dirting is typically not required when the conduit fill is 60% or less. This is because these wires typically carry low currents and do not generate as much heat as power conductors. However, if the conduit fill exceeds 60%, or if the wires are exposed to high ambient temperatures, dirting may be required. To determine the appropriate dirting factor, you need to consult the NEC tables. The NEC tables provide dirting factors for various conditions, such as the number of current-carrying conductors in a conduit or cable, and the ambient temperature. Once you have determined the appropriate dirting factor, you can multiply the ampacity of the conductor by the dirting factor to obtain the derated ampacity. The derated ampacity should not be less than the load current. Finally, let's explore cable trays. Cable trays are rigid structural systems used to support and route cables in industrial and commercial applications. They are typically made of metal or fiberglass and come in various sizes and configurations. Cable trays offer several advantages over a conduit, including greater flexibility, ease of installation, and better heat dissipation. The NEC allows for various types of cables to be installed in cable trays, including power cables, control cables, instrumentation cables, and communication cables. However, the NEC also specifies certain requirements for the installation of cables in cable trays to ensure safety and prevent damage to the cables. One of the key requirements is that the cables must be properly supported and secured to the cable tray. This prevents the cables from sagging or rubbing against the edges of the tray, which can damage the insulation. The cables can be supported and secured using cable ties, cable clamps, or other approved methods. Another requirement is that the cables must be protected from physical damage. This can be achieved by installing covers over the cable tray or by using cables with a rugged outer jacket. The covers protect the cables from falling objects, while the rugged outer jacket protects the cables from abrasion and impact. For instrumentation wiring, the NEC allows data cables, speaker cables, fire alarm cables, fiber optic cables, and low voltage switching cables to be installed in the same cable tray without any trouble. This is because these types of cables typically do not generate excessive heat and do not interfere with each other. However, it is important to ensure that the cables are properly separated and identified to prevent confusion during maintenance or repairs. The NEC also requires that the cable tray be properly grounded to provide a path for fault current in the event of a short circuit. The grounding conductor must be sized according to the NEC tables and must be connected to the cable tray at regular intervals. In summary, control wiring and instrumentation wiring serve distinct purposes within electrical systems. Control wiring transmits signals for direct equipment control, while instrumentation wiring connects sensors for measurement and monitoring. Conduit fill for both types of wiring can reach 60% without requiring current-carrying conductor dirting. Furthermore, instrumentation wiring can safely share cable trays with various communication and low-voltage cabling types, provided that proper installation and separation practices are followed.